All right, buckle up, everybody, because today we're taking a deep dive into the world of stellar giants,
Ooh,
the
exciting.
biggest stars in the universe.
Right.
And you've given us some pretty incredible research to work with here, so we're going to unpack what makes a star big.
Okay.
How does its size connect to its whole life, really? Its brightness, temperature?
Mhm.
Honestly, how can we even wrap our heads around the sheer scale of these things? I mean,
It really is a journey
it
that
is.
takes us from, thinking about things that are familiar, like our own planet,
Right.
to the very limits of what we understand about stars.
Yeah, speaking of Earth, it feels pretty big to us,
It does.
right? But when we start talking about stars, it's almost like comparing,
I
uh,
like where you're going with this.
I don't know, like a grain of sand to a mountain.
Oh, yeah, that's a good analogy.
Yeah.
An apt analogy. You've even included information on Jupiter in your research,
Yeah.
which is massive compared to Earth,
Right.
obviously. But to put things into perspective, if you took 90 Jupiters
Wow.
and you mashed them all together, you still wouldn't have enough mass to ignite a star.
90 Jupiters.
Yeah.
So is that the secret ingredient then? Mass.
Exactly. A star's mass is fundamental to its entire existence.
Okay.
It determines its size, its temperature, its brightness, how long it will live.
So what about those almost stars then, the brown dwarfs?
Mm-hmm.
I've always been fascinated by those.
Yeah.
They have enough mass to form, but not enough to really shine. Is that right?
That's the interesting thing about brown dwarfs.
Yeah.
They occupy this fascinating kind of middle ground between planets and stars, right?
Okay.
So they're more massive than a planet like Jupiter,
Right.
but they're not massive enough to sustain the same kind of nuclear fusion that powers a star like our sun.
And I noticed in your notes that adding more mass to a brown dwarf
Yeah.
doesn't make it much bigger.
It doesn't, does it?
So why is that?
It gets denser, you see. So
Yeah.
the pressure increases at its core. It's as though the added mass is compressing the brown dwarf, squeezing it tighter and tighter.
Oh, so it's like a cosmic pressure cooker then, just kind of simmering away.
I like that. That's a good analogy.
So when we talk about actual true stars, where do we start on that spectrum?
Well, we got to start with the smallest of the bunch, right?
Okay.
The red dwarfs.
Okay.
Now, these are the most abundant type of star in the universe,
Yeah.
and for good reason.
Okay.
They're incredibly efficient.
Right.
They slowly burn their hydrogen fuel over trillions of years.
Trillions. Wow.
That's a long time.
That makes our sun seem like a gas guzzler.
It kind of does, yeah.
But speaking of the sun, where does it fit in all of this? I mean, we're pretty familiar with it, right? Its size, its brightness.
It's a good reference point.
Yeah.
The sun is an excellent example of a main sequence star.
Okay.
It's a yellow dwarf.
Mm-hmm.
And like all main sequence stars, it's in this stable phase of its life, fusing hydrogen into helium at its core.
And, it really dominates our solar system, right?
Oh, yeah.
99.86% of the mass of the solar system is the sun.
That's right.
I remember seeing that.
It's the gravitational anchor of our entire planetary system.
Sure.
But even our sun, which seems so colossal to us,
Right.
it's actually relatively small compared to some of the stellar giants out there.
So let's talk about some of those bigger stars then.
Yeah.
You mentioned Sirius, the brightest star in our night sky.
Yeah.
And Beta Centauri, a binary star system.
Hmm.
What makes these stars stand out?
Well, they're all main sequence stars,
Okay.
but they're significantly more massive than our sun.
Right.
And as we've said, mass is key.
Yep.
These stars burn hotter, they burn brighter, and they live much shorter lives.
So you've mentioned this idea of a trade-off a couple of times now, like brightness and lifespan.
Right.
It seems the bigger and brighter a star is, the faster it burns through its fuel.
It's a fascinating cosmic balance.
Yeah.
Take Sirius, for example. It's only twice the mass of the sun,
Yeah.
but it shines 25 times brighter.
Wow.
However, it's only going to live for a few billion years
Right.
compared to our sun's, 10 billion year lifespan.
So even small increases in mass have a dramatic effect.
They do.
And Beta Centauri, with stars 10 times the mass of the sun, those are even more extreme. Right?
Absolutely.
Yeah.
Each star in that system shines with about 20,000 times the power of the sun.
Oh, wow.
That's a staggering amount of energy.
Yeah.
But they'll only last for about a cosmic blink of an eye, really, about 20 million years.
It's really amazing how much we can learn about a star just by knowing its mass.
It's true.
It's like a key that unlocks its entire story.
Yeah.
But you mentioned one main sequence star that really pushes the limits, R136A1.
Oh, yeah.
What makes it so unique?
R136A1 is the most massive star we know of.
Okay.
315 times the mass of the sun.
315 times. I can't even imagine that.
It challenges our understanding of how stars even form.
But it's not even the biggest star out there, is it?
Well, R136A1 is unbelievably massive, yes.
Right.
But it's actually only about 30 times larger than the sun.
Oh,
To
about.
find the truly gigantic stars, the
Right.
ones that dwarf even R136A1, we have to look beyond the main sequence.
Beyond the main sequence. Does that mean we're talking about stars that are dying?
In a way, yeah.
Yeah.
As stars age, they go through incredible transformations. They can swell to sizes that are truly mind-boggling.
Okay.
It's a phase of stellar evolution that's as spectacular as it is dramatic.
All right. So what happens when a star, say one like our sun, starts to reach the end of its life?
When a star like our sun runs out of hydrogen fuel in its core,
Right.
things get very interesting.
Okay.
The core contracts, becoming hotter and denser,
Mm-hmm.
and this triggers the fusion of helium into heavier elements.
So it's like it switches gears, starts burning a different type of fuel?
Exactly. And this new phase has a dramatic effect on the star's size.
Oh.
It swells up, becoming a red giant.
Wait, so our sun is going to become a giant. How big are we talking?
Our sun, when it becomes a red giant, will expand to about 200 times its current radius.
200 times.
Yeah.
That's enormous. But are red giants the biggest stars out there?
No.
Okay.
Red giants are impressive, yeah.
Right.
But they're just the stepping stone to the truly colossal hypergiants.
Hypergiants.
These are the giants of the giants.
Okay, I read.
Stars so large that they push the boundaries of what we thought possible.
All right, what makes them so different from red giants?
Think of hypergiants as red giants on steroids.
Okay.
They have such a massive surface area that they radiate incredible amounts of light and energy.
So not just bigger, but brighter, hotter, more intense in every way.
Exactly.
Oh.
But their immense size also makes them somewhat unstable.
Uh-oh.
They're constantly shedding material, almost like they're struggling to hold themselves together.
That sounds intense.
It is.
Are there different types of hypergiants?
There are. One example is the Pistol Star,
Okay.
a blue hypergiant.
Okay.
It's named for its incredibly energetic blue starlight.
Right.
It's about 25 times the mass of the sun,
Oh.
but a staggering 300 times its radius.
300 times the radius of the sun. Okay, now things are starting to get really hard to picture.
I know, it's hard to comprehend.
Yeah.
You also included information on yellow hypergiants like Rho Cassiopeia.
Right.
It's so bright you can actually see it with the naked eye,
Really?
even though it's thousands of light years away.
Visible from Earth despite being thousands of light years away. That's incredible.
It is.
But how big are we talking?
Rho Cassiopeia is about 40 times the mass of the sun and roughly 500 times its radius.
Okay.
To put that into perspective, if Earth were as close to Rho Cassiopeia as it is to the sun,
Right.
we'd be inside it.
We'd be inside it. So that's bigger than our entire solar system.
It is.
What could possibly be larger than that?
That brings us to the reigning champions of size, the red hypergiants.
The red hypergiants. Okay.
These are the largest stars known,
Right.
and possibly the largest stars that can even exist.
The name itself sounds epic.
It does, doesn't it?
What are we dealing with here?
Red hypergiants are truly incredible.
Okay.
They push the limits of stellar size and luminosity,
Mm-hmm.
shining with a power that's hard to imagine.
So why are they so hard to measure? You'd think something that big would be easy to spot.
Well, they are incredibly distant,
Okay.
and because they're constantly shedding material, their boundaries can be a bit fuzzy.
It's kind of like trying to measure a cloud that's constantly changing shape.
Exactly. It's a challenge.
So even with all those challenges, do we have a candidate for the title of biggest star?
We do.
Okay.
The current frontrunner, at least for now, is a red hypergiant called Stephenson 218.
Stephenson 218. Yeah, I remember seeing that in your research.
Yeah.
What makes this star so special?
It's a true behemoth. It likely started out a few tens of times the mass of the sun, but has shed about half of its mass already.
Okay.
While typical red hypergiants are about 1,500 times the size of the sun.
Right.
Stephenson 218 is estimated to be a mind-boggling 2,150 solar radii.
2,150 times the radius of the sun. Okay, now I definitely need a minute to process that.
Yeah,
I mean, how can anything be that
it
big?
is hard to grasp, but let's try some comparisons.
Okay.
It would take light,
Right.
the fastest thing in the universe,
Mm-hmm.
8.7 hours to
Yeah.
travel around Stephenson 218 just once.
8.7 hours for light to go round at once. That's more time than it takes for me to get through a workday.
It's a long time.
Yeah.
Think about the fastest plane on Earth.
Okay.
To circle this star, it would take around 500 years.
500 years. And to think, we used to think Earth was the center of the universe.
It really puts things into perspective.
It does.
Speaking of perspective, if we were to somehow place Stephenson 218 in our solar system,
Okay.
it would fill Saturn's orbit.
Saturn's orbit, that's beyond comprehension.
It's hard to wrap your head around.
It's like trying to picture an ant carrying a house.
Yeah.
I don't think my brain is equipped to handle this kind of scale.
It certainly challenges our perception of reality.
That's a good way to put it. Maybe after a break, we can continue exploring this mind-boggling star and what its existence tells us about the universe. All right, I think I've had a moment to let that sink in Saturn's orbit. It's amazing that a star like Stephenson 218 can even exist.
Yeah.
But I'm curious, even something that massive, it can't last forever, can it?
You're absolutely right. Even a star as colossal as Stephenson 218 is bound by the laws of physics and the cycles of stellar evolution.
So what's in store for a star like this? Does it just keep getting bigger and bigger and bigger?
Actually, as it continues to burn through its fuel, it's likely to shed even more of its mass,
Oh, okay.
eventually shrinking down into a hotter, denser phase.
Shrinking. I thought we were talking about giants.
It might sound counterintuitive, but as it sheds those outer layers and its core contracts, it will actually become smaller and hotter. It's a bit like a phoenix rising from the ashes.
Okay.
But instead of fire, it's fueled by nuclear fusion.
So it's not just about size then.
Right.
It's about how the star evolves over time.
Exactly.
You mentioned that it accumulates heavier elements in its core as it ages.
Right.
What role do those elements play?
That's a crucial part of the story. As a star like Stephenson 218 fuses lighter elements into heavier ones, it's essentially creating the building blocks for the next generation of stars and planets.
You've mentioned this idea of a cosmic cycle before.
Yeah.
It's almost poetic. A star is born from a cloud of gas and dust.
Right.
It lives its life. And then, in its death throes, it seeds the universe with the ingredients for new stars and planets.
Exactly. And the more massive the star, the more dramatic its death.
Yeah.
In the case of Stephenson 218,
Okay.
it will eventually reach a point where it can no longer support itself against gravity.
Okay.
And when that happens,
Yeah.
it will
Yeah.
explode in a spectacular supernova.
A supernova. So that's like the grand finale,
It is.
the ultimate cosmic fireworks show.
You could say that.
What would that even look like?
Imagine a sudden burst of light,
Okay.
so bright that it outshines an entire galaxy.
Wow.
That's the power of a supernova. It's a cataclysmic event that releases an unimaginable amount of energy
Right.
and scatters the star's enriched material across vast distances.
So even in death, a star like Stephenson 218 plays a vital role in the cosmic ecosystem.
It does.
Like its final act is to give back to the universe,
Right.
provide the material for new stars and planets to form. It's
Yeah.
pretty amazing when you think about it.
It really is. It highlights the interconnectedness of everything in the universe.
Yeah.
The material that makes up our bodies, the earth beneath our feet, even the air we breathe,
Yeah,
all came from the heart of a star that lived and died billions of years ago.
that's a humbling thought. We're all made of stardust, quite literally. It's incredible how studying something as vast and distant as a star can connect us to our own origins. But I'm curious, we've talked about a lot of different types of stars today. From brown dwarfs to red giants and hypergiants.
Right.
Is there a limit to how big a star can get?
That's a question that astronomers are still grappling with. While we haven't found anything larger than Stephenson 218 yet,
Right.
it doesn't mean that even larger stars couldn't exist.
So there could be even more massive giants lurking out there in the depths of space, just waiting to be discovered.
Absolutely. Our understanding of the universe is constantly evolving. New discoveries are being made all the time, and what we consider the biggest or the most extreme today could easily be surpassed tomorrow.
Right.
Remember, we're just beginning to explore the vastness of space.
It's exciting to think about what other mysteries the universe holds. But I have to ask, is there anything even bigger than a star? What about those black holes I keep hearing about?
Black holes are a fascinating topic, and they are definitely in the realm of the biggest and the most extreme.
Okay.
They're regions of space-time where gravity is so strong that nothing, not even light, can escape.
Wow, so even a supergent star would be no match for a black hole.
Not at all. If a star gets too close to a black hole, it can be torn apart and consumed by the black hole's immense gravitational pull.
That's both terrifying and fascinating. It's like a cosmic dance of creation and destruction with stars and black holes playing their parts in this grand cosmic ballet. But I have to ask, are black holes just giant vacuum cleaners sucking up everything in sight?
Not quite. While black holes do have incredible gravitational pull,
Right.
they don't just randomly gobble up everything around them.
So they're not as scary as they sound.
They're certainly powerful objects, but they play a vital role in the evolution of galaxies,
Okay.
including our own Milky Way.
That's amazing. We've come a long way from talking about brown dwarfs to black holes. It's incredible how everything is connected in the universe.
It is.
But I have to ask, you've mentioned that our understanding of the universe is constantly evolving.
It is.
What are some of the things that astronomers are still trying to figure out about stars?
There are so many questions we're still exploring.
Like what?
For example, we don't fully understand how the most massive stars, like R136A1, form.
Right.
Their size and mass push the limits of our current models of star formation.
So there's still a lot we don't know about these stellar giants.
Absolutely. And that's what makes astronomy so exciting. There's
Yeah.
always something new to discover, something new to challenge our understanding of the universe.
And speaking of challenging our understanding, what about those mysterious dark matter and dark energy that we hear so much about? How do they fit into this picture?
Dark matter and dark energy are two of the biggest mysteries in cosmology today.
Okay.
They don't interact with light,
Right.
so we can't see them directly, but we know they exist because of their gravitational effects on the visible universe.
So it's like we can see their footprints even though we can't see the creatures themselves.
Exactly. We know that dark matter makes up about 85% of the matter in the universe.
Wow.
And dark energy is thought to be responsible for the accelerating expansion of the universe.
That's mind-boggling.
Yeah.
We've spent this entire deep dive talking about stars.
Right.
But it turns out that most of the universe is made up of something we can't even see.
It's a humbling realization.
Yeah.
It underscores how much we still have to learn about the universe.
Right.
But it's also an incredible opportunity for discovery. Imagine the breakthroughs that await us as we continue to probe the mysteries of dark matter and dark energy.
It's almost like we've just opened the first page of a vast cosmic book.
Yeah.
And we're eager to see what stories unfold in the chapters to come. But before we get ahead of ourselves, maybe we should take a step back and reflect on what we've learned about stars. These incredible beacons of light that illuminate the vastness of space. You know, it's really amazing to think about the journey we've taken today, from our own planet to the farthest reaches of space, exploring this incredible diversity and scale of stars.
Yeah, it's a journey that highlights not only the vastness of the universe, but also the intricate ways in which everything is interconnected.
We started with those almost stars, the brown dwarfs.
Right.
Then we explored the main sequence stars, you know, like our own sun, before venturing into the realm of giants and hypergiants. And along the way, we've uncovered these fascinating insights into how stars are born, how they evolve, and how their deaths contribute to the creation of new stars and planets.
It's a cycle of cosmic creation and destruction that's been playing out for billions of years, shaping the universe as we know it.
And it all comes down to mass. This seemingly simple property that dictates a star's entire life story, from its size and brightness to its lifespan and ultimate fate.
Mass is the fundamental driver of stellar evolution. It determines the forces at play within a star, the rate at which it burns its fuel, and the types of elements it creates in its core.
You mentioned earlier that the material from supernova explosions eventually forms new stars and planets. It's incredible to think that the atoms in our bodies were once forged in the heart of a star that exploded billions of years ago.
It is a profound thought, isn't it?
It is.
We are, quite literally, stardust.
Yeah.
And this connection to the cosmos extends beyond our physical bodies. The very elements that make life possible, like carbon, oxygen, and nitrogen, were all created in the nuclear furnaces of stars.
That's incredible. So in a way, we owe our existence to these stellar giants that lived and died long before our planet even existed. It makes you wonder what other secrets are hidden within those distant points of light.
There's still so much we don't know about stars, especially those at the extremes of size and mass.
Yeah, like how do the most massive stars even form?
Right.
What are the limits of stellar size?
These are questions that astronomers are actively working to answer.
And what about those black holes we talked about earlier?
Mhm.
What role do they play in the grand scheme of things?
Black holes are still shrouded in mystery,
Right.
but we're learning more about them all the time.
Right.
We know they play a crucial role in the evolution of galaxies,
Mm-hmm.
shaping the distribution of stars and gas. And some scientists believe that supermassive black holes, the ones found at the centers of most galaxies, may even have played a role in the formation of the universe itself.
That's mind-blowing. It seems like every time we think we're starting to understand the universe, we just uncover even more mysteries.
That's the beauty of science. It's a never-ending quest for knowledge.
Mm-hmm.
And the more we learn, the more we realize how much more there is to discover.
Speaking of discoveries, I remember reading in your research about this idea of a habitable zone around stars. What is that exactly?
The habitable zone, also known as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on the surface of a planet.
Okay.
It's not too hot, not too cold, but just right for life as we know it to potentially thrive.
So finding a planet in the habitable zone of a star would be a pretty big deal.
It would be a monumental discovery. It would increase the likelihood of finding life beyond our own planet, which would be one of the most profound discoveries in human history.
That would certainly change our perspective on our place in the universe.
Yeah.
But finding a planet like that, it's like finding a needle in a cosmic haystack, right?
It's definitely a challenge, but astronomers are developing increasingly sophisticated techniques for detecting and characterizing exoplanets, planets orbiting other stars.
Okay.
With missions like the James Webb Space Telescope, we're getting closer than ever to finding another Earth-like planet out there.
It's exciting to think about the possibilities.
Right.
And it all comes back to those stars, those distant suns that hold the keys to understanding our place in the universe and the potential for life beyond our own planet.
It's been a fascinating journey exploring the world of stellar giants, hasn't it?
It really has. I feel like I've learned so much about these incredible objects and the vastness of space.
And I hope it sparked a sense of wonder and curiosity in you, our listener. The universe is full of mysteries waiting to be uncovered, and who knows what amazing discoveries lie ahead.
Absolutely. On that note of cosmic mystery and the endless possibilities of exploration, I think we'll wrap up our deep dive for today. Thank you so much for providing such fascinating material and for joining us on this incredible journey.
It's been my pleasure. Until next time, keep looking up at the stars and keep asking questions. The universe is waiting to be explored.